Okay, let's talk a little bit about linear momentum. So consider for a second just a simple case of motion here. We have an object of mass m that is sliding along at speed v, velocity v specifically. We've talked about this a lot. Just things moving. It's not accelerating, not doing anything weird, just object mass m, velocity v. Now we know when we talk about this, Newton's first law, an object in motion will stay in motion, object in rest will stay at rest. Well, unless acted upon by a net external force. Sorry, compulsion. Let's focus on what we mean by in motion for a second. In the past, we've taken this to mean that it has a velocity. This is not entirely true. It does mean, for something to be in motion, it does in fact have to have a velocity, or else it's not really in motion. But let's think about this for a second in a little greater detail. The real criteria that we're discussing is that something is in motion, staying in motion, at rest, staying at rest, unless acted upon by a net external force, which means that its motion will change if there is a net external force. So we've written that down in the past as F net equals ma. An object will accelerate, its velocity will change. But what we can do is look at this slightly differently and expand kind of our definition. So A is dv dt. Yes? Imagine for a second that we're going at constant mass. If we're going at constant mass, then this m can pop right back into the derivative. If we do this, what we're going to see is this new combination that's going to be useful for us. This quantity mv. And this is really what we're interested in changing. We've always taken the case kind of tacitly that we're looking at cases of constant mass, where the mass is not changing. But if we now say, well, let's just kind of take a general case. Well, if we take a general case, let's kind of take that step back, put the mass back into this derivative, and allow ourselves to ask, well, what would happen? Well, this mv is going to be what we're going to call the linear momentum. And the linear momentum we're going to label as p, and it will be equal to the mass of an object times its velocity. Having done this, we can now say that F net external, the net external force on an object, is equal to dp dt, the rate of change of momentum. All right. This also has one other wonderful thing. So consider the case where F net external equals 0. So we have a situation where there is no external force on an object or on a system of objects. The system of objects bit is what's going to be really key here. Because if I have two objects, say for example, two balls, we'll come back to this in a second. If I look at one ball hitting another ball, and they are separate objects, I'm only focusing on this M1, this ball 1, then there is an external force. It has some contact with ball 2, and that's, quite frankly, complicated. We don't really have a model for what it means to collide with something. But let's say I take the system instead to have both balls in it. In that case, that collision, that force that happens, that's going to be whatever force, it's an internal force. So if it's an internal force, then the external forces, we don't have any that we're talking about really, ignoring gravity, normal force, stuff like that, which would presumably be balanced on a level surface or in whatever magical space we're considering. If the net external force is 0, then dp dt is equal to 0. So the momentum is equal to a constant. What this is saying is that momentum is conserved when there's no net external force. Furthermore, we can be sneaky about this. Momentum can still be conserved even when there is an external force, as long as the collision happens over such a small time that it doesn't really appreciably act. So consider this case now. I have m1 v1, some velocity, colliding with m2 v2. So the way that I'm going to look at this is just like when we're talking about energy. I'm going to have an initial state, and I'm going to have a final state. In my initial state, I have some initial momentum for the first object, which looks like m1 v1. I have some initial momentum for the second object, which looks like m2 v2 initial, which as I've drawn it is just 0. So now after this collision, any number of things could happen. You could imagine, the first ball stops, second ball goes. You could imagine first ball recoils. Second ball goes forward. You could imagine both balls stick together and go forward. Any number of possibilities can occur. So the question that we have to ask is kind of, can we determine a framework to discuss this? Well, in the final state, there will be some final momentum of the first ball. And some final momentum of the second ball. Okay, there was a slight interruption there. I'm going to hope that I remember what I was saying before, which I assume was that I had a final momentum, which I should put arrows on, for my second particle. So now, if momentum is conserved, because there's no net external force, that means that our initial momentum must equal our final momentum. This is a little more prickly than conserving energy, because we're dealing with vector quantities. So right now we have a 1D case, but we can expand this to a 2D or 3D case, or to a many object case as time goes on. So in this simple case, m1 v1 initial, second object's at rest, has no momentum to start with, equals m1 v1 final plus m2 v2 final. Yeah. So now, if you know the masses, the initial momenta, you can begin to solve this a little bit. You do need to know a fair amount of information, but it is quite doable. We're not going to do a specific example right now because I want to keep pushing along. The other thing we need to talk about in terms of momentum, if we go back again to this definition, F net equals dp dt. We said if F net is 0, then there is no change in momentum. Momentum is constant. But what if it's not 0? Well, then I can look at this and I can say F net dt equals dp. If I integrate these, what I'm basically going to get is that the change in momentum is the integral of the force with respect to time. And so this we're going to call J the impulse. We're really good with labeling. And so when we think about, a collision basically, or if you're catching something, like if you wanted to have an egg drop, this is the physics behind it, is that you have a fixed momentum for an egg drop, or a fixed delta P really, right? Because you have an egg. It's not really a good egg, I'm sorry. You have an egg, and it is dropping and is about to splatter. So right before it hits the ground, it definitely has some momentum due to its velocity, and then when it hits the ground, it has stopped. So there is some definitive delta P. Now the question is then, if we have a fixed delta P, that means we have a fixed impulse. So how do we manage to minimize the force? Well, you can minimize the force, the average force, at least by maximizing the time. You make a collision take longer. So this is to some extent the idea of airbags, of cushions, things that cause a collision to not just be, smack, but to be smush. Anyway, food for thought. I really should have had snack or something, because apparently eggs and food and anyway. Point is, this is all trying to get this idea of linear momentum and cases where we are going to conserve linear momentum. All right, this is an excellent tool in moving forward. It allows us now to expand our range of study from single objects that have a force acting on them to objects that collide, that explode. Or explosion is also going to be an absence of an external force. And so that's going to really kind of open up a new realm of opportunities for us. Cases where it was kind of difficult to pin down what exactly was happening. We could talk about average forces and things like that, but now we can ignore it entirely by just saying, oh, well, whatever happens, we get kind of this Newton's third law thing going on. And the way that we're summing up these results is in terms of momentum conservation. So whatever, if I kick something, I get kicked back a little bit. There has to be some, the mechanics of that have to add up and respect this conservation law. All right, hopefully that helps kind of get you started with this. You want to take a look at the center of mass one also to look at exploding cases. See you later.